Good. Yeah, I started recording. You can start.
Okay. Yikes. I apologize in advance. Okay, hopefully that doesn't fall. Hard aroma. Wait, is this yours?
I just bought this. I just.
Okay, I was about to say, I thought someone just left like $40 a shot.
That's not $40. That's much.
Yeah. Oh my god, Sensei, please.
I bet. We're gonna do the harmonic oscillator. Yes. So we start with the Hamiltonian in classical mechanics, which I'm actually gonna try to remember. X squared. That's supposed to be squared, right? Because it wasn't squared on the.
Oh, it wasn't?
Yeah, but
Yeah,
I'm pretty sure that's supposed to be squared. Okay.
Of course it's squared.
Perfect. Now we take the Hilbert space, just like last time, or not last time, the time before that time, but the last time I went. And that's going to be the square integral functions, which is just like the. Yes, that. And we're going to quantize H, which means this P is going to become negative I at X, and X is.
Also, no one's in a rush, right? According to
No,
the me. Okay, good.
Nope.
So, first question. Before we go to the quantum world,
Yeah.
so why is everything a harmonic oscillator?
It's just the beauty of life.
No, why is it x squared?
Oh. It's I got this. Oh, this was on the last physics test. I forgot it. The
Okay, can you draw me, so go to the right hand corner, yeah, and draw for me y equals x versus y equals x squared. Okay, that's y equals x. That's y equals x squared. Okay, beautiful. What's the difference? What's the difference?
Oh.
Okay.
Is it because y equals x can be negative?
Okay, sure, but that's right. I guess I want a particular statement. Okay, what happens at 0 to x squared? The derivative is 0, which means that there is a
minimum?
Minimum, there we go. There's a minimum. Okay, great. So remember, what was this x squared thing? Physically, what did that mean? That was the what?
Kinetic energy?
The x squared was the kinetic energy? No, come on, please.
The potential energy.
It's the potential energy. There we go. So remember, harmonic oscillator was for a mass on a spring. Do you agree?
Yes.
And so you got that you had kinetic energy p squared over 2m, and then this was the potential energy. Okay?
Yeah.
In general, suppose I had some arbitrary potential.
Mm-hmm.
Okay? I had, whatever, arbitrary system. Okay? But suppose I was interested in some low energy limit of this, of studying the system. I wanted to do it in the low energy limit. So if I'm in the low energy limit, that means I have to be at some sort of minimum of my energy.
Yeah.
Do you agree?
Mm-hmm.
And from Math 157, you know that you can, if you have a nice enough function, you can write it down as a Taylor series.
Mm-hmm.
Okay. And if I'm at around the minimum, do you agree? Okay, at the minimum, the derivative is 0.
Mm-hmm.
So I can Taylor expand and always argue, okay, if I am confined because I can't have too much energy to stay within this region, do you agree? Then my potential over there will look like a parabola.
Yeah.
Do you agree? So to some first order approximation, my energy will look like this.
Yeah.
So why is everything a harmonic oscillator? Because if I look at any potential and I want to look at some low energy limit and expand it around the minimum, that will just be the first order term. Okay?
Mm.
That's it. So when people say everything is a harmonic oscillator, it's like, yes, because if you expand the function around the minimum, the first order term is an x squared term. That's it. Okay, yes.
That's just our approximation.
And I mean, that's usually the approximation. In some cases, like for mass on a spring, it's a really good approximation. But in many cases, that's just the approximation that people make.
Mm.
The other thing is this quadratic thing is actually, the harmonic oscillator in like almost every universe is, in almost every case that you encounter the harmonic oscillator is one thing that you can solve exactly.
Mhm.
Like you can fully solve the problem. And then that's like, usually ends up also being the only interesting thing that you can solve exactly. And so then everything you do, you essentially becomes, let's try expand around the low, the energy minimum and, okay, whatever, move on. Okay, does that answer a question no one asked? Good. Right, so this is the classical energy. It's classical in what sense? It's classical that this is a function of what, two variables?
The position and the momentum.
And the momentum, good. And yeah, that's good. So now you want to go to the quantum mechanical case, and what do you want to do?
Replace the momentum with the derivative of the.
Sorry, I want more basic. I want, before h was a function from p and x,
Yeah.
now I want h to be before h was a function of p and
Yeah.
x.
Of
Once
the
I go to
state.
the quantum world, I want h to be
It's like that.
Which
You got it.
H?
that p squared over 2mh.
The Hamiltonian.
The Hamiltonian.
Hamiltonian.
I now want it to be what kind of object?
The state.
Linear operator.
Yes, what kind of linear operator?
Self-adjoint.
A self-adjoint
Hermitian.
linear operator acting on what Hilbert space?
The square integral.
Yes, square integral functions. Very good. Okay, and so the process. Okay. Okay, that's right. Typo. Derivative squared. So what is this mx thing?
It's just x, right?
This has to be what kind of object? This has to be a
Linear operator.
linear operator that acts on functions.
Yeah.
How does mx act on a function?
It multiplies it by x.
It multiplies it by x.
Yeah.
Good. So I wrote it as an x last time, just to be very clear as to what, that this is a multiplication operator. However, nobody in physics ever writes mx, ever.
Oh shit.
Everyone just writes x still.
Alright.
So keep it, write it again, but in every future instance,
Mhm.
instead of writing mx, write x.
Indeed.
But the first time I introduced it to you, I just wanted to be more clear as to what the notation means. Okay. Yeah. So we'll just now use this notation whenever I have something that's just x, or some function that's just a function f of x. I mean the operation of multiplying a function by this function. Okay, very good.
Is that right?
Well, what is that?
Wait.
What are you trying to do?
I just wrote it so that I understand it.
Okay, yeah, but what's the last bit in equals e?
I don't know.
Erase that for now then.
Okay.
If you don't know what that is, erase it for now. Okay, there's a question.
H of psi is a Hermitian of psi, like the state.
What do you mean?
Like, what is H of psi is the
That's the function in
the
the.
okay.
H applied to psi. H is a
Yes.
linear operator, psi is a vector.
Yes.
So that is what it is.
Okay.
Wait, I need to
If you apply h to some function psi of x,
Mhm.
then you get that. You get a minus h squared second derivative
Yes.
plus
okay.
1/2, whatever the rest is.
I bet.
Okay.
So now we have an ODE, but apparently this is really hard to solve. So we're gonna
Hold
use
on,
other
hold on.
methods. Yes.
You're You're going so fast. I can't keep up. This is too fast for me. So okay, we wrote down a Hamiltonian.
Yes.
Do you agree? What do we want to do now?
The
Conceptually.
eigenvalues.
Why do we want to find the eigenvalues?
That the energy states.
Yes, the eigenvalues tell me the possible energies. Okay, so these are things you should say. Instead of just
So
doing
we
a
want to
calculate-
find the eigenvalues of this linear operator, so we can find the possible energy states.
Okay, and so to find the eigenvalues, I need to solve what equation?
This one. The.
Well, you don't
you
write
need
the
to
whole thing.
find like that.
So write the simple equation. Eigenvalues of a linear operator means that h of psi is equal to. Okay, beautiful. So we want to solve this equation. Okay.
Okay. Bad. But I don't know. On the notes, it just says that we can't do it directly from here. Apparently.
We can. It's just that there's a much more clever and insightful way to do it. So I
Yeah.
think the first time when people did it,
Yeah.
they actually just solved this ODE,
Yeah.
and you get what's the polynomials that you get? There's like the one of the polynomial things that you get are polynomials that you get in the solution of this equation. But we'll see them anyway.
If you have like if this was equal to like just this, then you'd have like the sine and cos one, right? Because it'd be the second derivative plus the derivative plus the function itself is
Sorry,
equal
say
to
this
0.
again?
Like if there wasn't this term, and then you just had like something over here, then you could just like then that it would be like easier to solve, right?
So, yeah, look, if you didn't have the interacting the x squared term, right?
Yeah.
If you didn't have a potential,
Yeah.
then what would we reduce to essentially?
Like the
What
sine.
did we do the previous time?
Oh, the particle in a box.
We did a particle in a box. What was the potential for a particle inside the box? Yes.
0 and infinity.
Yeah, it was
outside.
0 on the
Oh,
inside
yeah,
and infinity on the outside.
yeah.
But we solved the equation for 0 on the inside, which would have been the exact same thing, but without the
This, right?
without the second term, right?
Yeah.
Because there was no potential. And remember, what did we get in the solution that time? It was sine and cosine.
Yeah.
However, the important part there is that my state was restricted to a box. So it was sine and cosine and kind of 0 everywhere else, right? And so that was something that had finite norm. Do you agree?
Yes.
Like if I just took a sine and cosine and tried to integrate that over the entire space, I'm not going to get something finite. So it's kind of there's a lot of words to be said about a free particle in just free space, at least from the mathematical viewpoint. But sure, okay. So we want to solve this equation now.
Yes.
Yes. Continue.
Okay. So the first step to do this, I'm gonna be honest, I don't know why we do the steps, but I know it works out at the end. But the first step is to find the commutator of this.
Okay.
Ooh, I just got chest pain. I think I'm dying. Just
Yeah.
yes.
Yeah.
And then we can just plug some stuff in now. That's x, because we're just multiplying, and then we plug in this over here. I'm gonna run out of space. Can I just use a new board?
It's your presentation.
It's kind of nice.
The other thing that you could do is, if you're going to use anything that's written over there, you could just write on this board and like turn the laptop,
turn the
maybe
laptop.
shift the table a little bit.
Bad.
Do something like this. Okay. Beautiful.
I'm just gonna write it out. Okay, so that's x, negative I, chat, dx, minus negative I, dx, x. So, if you were to do this to a function, yes, then this is just literally negative I, x, dx. And then this one here is you have to derive. Wait, did I just backwards?
No, I didn't.
You have to derive x and also like whatever function is here. So then that would be first derivative of this, and the derivative of x is 1, and then plus no, whoops, x, and then yeah, like that. And then you have your negative I half, negative I. And then
did you have minus minus?
oh, oops. Okay, and then this part and that part cancel out, and then you're just left with IH.
You're missing one last thing. IH.
Wait, what?
Psi, right? You
Oh,
still
yeah.
have psi. Okay. And so then what you get is so this is you applying the things, the operator to a function.
Yeah.
What is the operator itself? Just write it equal. So go back there.
Like,
No, erase this. Sure. Go back there. You wrote x comma p.
Yeah.
Like just write it as an operator now. No. Don't add the sign. Don't add the sign. You have some
Yeah.
operator x comma p.
Yeah.
X comma p, right?
Yeah.
And there you computed how it acts on a function.
Yes.
Okay. What is this operator? You just computed what the operator is. What is this operator?
That?
What is it? Write down an expression for this operator. So how did this thing act on a function? What did it do to the function?
It multiplies it by I and
I and h bar. Okay, so this means that this can be written as the identity operator times.
Oh.
Okay, perfect.
I get
so
it now.
replace the x minus I over there. Yes. And then just write I h bar and then identity. Okay, good. Yes. So actually, my personal preference, advice would be, right now, you're going to be computing a bunch of stuff, right?
Yeah.
And it might make a lot of sense to kind of use that board to keep track of the results that you get, and then use this board to do the calculations. So I would take this eraser, keep that stuff, erase the picture, and where the picture is, I would like just write stuff like just write something like that. Good. And maybe the definitions of some things. Good. So and erase the bar. So now let me maybe explain what it is. Erase erase the other red part. Now I'll maybe explain what we're trying to do. So we want to write down, figure out what the spectrum of H is. We want to find the eigenvalues. And when you look at the when you look at that, that operator, that looks kind of confusing. Like I don't know, it's not immediately obvious to me how this works. And so instead, what we're going to try and do, we're going to try and it's almost like a change of basis. I'm going to try and come up with new operators, and I'm going to rewrite my Hamiltonian in these new operators, and hopefully it's going to be more obvious how those guys work. And you'll just kind of see how this works out. It's kind of not immediately obvious that this is the right thing you have to do, but this is something that will then appear in quantum mechanics over and over again, this exact same kind of idea. Okay, sorry, keep going.
Okay, the next step. Oh my god, I have no idea what happened. But like, I think they replaced x with the rescaling by HIH. Is that right?
It's not x is not rescaled by IH. It's rescaled by like some square root m omega something.
Okay, we tried to work it out, and she told me this is what it is, but I have no idea. That's what I wrote. She said rescale by this, and that's that, and then we'll get what you want.
Okay.
But we weren't sure.
it doesn't matter whatever the rescaling is.
Yeah.
The point is, so just skip this part. Skip the how to do the rescaling. You
Yeah.
can look it up in the Wikipedia. The point is, you can rescale your x coordinates such that the new Hamiltonian, actually maybe even just erase this, all of this, and write it in white in the center. That the new what the new Hamiltonian is going to be like.
Also, the 1/2 is supposed to be on the outside, right?
The one is should be 1/2 x.
Because it's on the inside here.
Yeah, of course it's on the outside. Yeah, of course it's on
This
the outside.
took us so long to figure out, by the way.
Okay. Yeah. Of course it's on the outside.
Okay.
She told me that it took a while. So I'm just gonna tell you that you can do this.
Yeah, so this does happen if you
Yes.
rescale I. And
You-
then what you do is there's usually like a H bar omega that would be right there.
Yeah.
But you just change your units for that to be 1. So then you
Yeah.
can just ignore it.
You can change your energy units to be in terms of H bar omega. Yeah.
Okay.
Do people kind of believe that I can get that? Right? I mean, even when you solve the harmonic oscillator classically, right, you also do a similar kind of rescale. Okay.
Okay. And then we're going to define these two things. Should I define them?
I think you should define them there and then do all computations over
Okay.
there.
So the annihilator, I think?
There's the creation
Creator,
operator.
the creation operator, and the annihilation operator.
Yes.
And
Not to be confused with the annihilator in like dual spaces. Completely
Yeah,
unrelated.
yeah.
Wait, these are cool though. They're like, that low-key makes sense. I saw like this one ladder. We'll get to that. It's pretty cool. It's pretty cool.
Anyways, okay, so this one, which is the
A dagger is the creation one.
and this is 1√2 x minus I.
Yes.
And the other one is the same thing, but what's that thing?
And then what you gotta realize is that these are actually a joint because these are a joint to themselves, and you can just take like the conjugate transpose of like the whole thing and then just flip it, and then the I will be the only thing that swaps because this is real. And then, does that make sense?
Yes.
Alright, chill. And then we're gonna compute the commutator of this direction, like that. I guess I'll do that over here actually.
Oh, right. Also, the other thing, I guess it doesn't matter here, but I think we also set H bar equals to 1.
Oh yeah, we did.
We said, so it's not just we set H bar omega is equal
Because
to
we
1.
go back
We set
here.
H bar equal to 1 and omega is equal to 1.
Yeah, so then when you go
But-
back here, this just becomes
Yes.
I
Yes.
because of this.
Yes.
That's pretty important, Loki. Okay. And then this part here, we're gonna show that this is, what are we doing? Is just gonna be 1. So to do that, we just plug in everything, which is. Oh, actually, one sec. Where is it?
Here, can you show me your microphone for a second that I see is blinking green? Yeah, good. Thanks.
We're actually not gonna do it. Or we're gonna leave it in this one. We're gonna make this 1√2 x minus IP, and then
Very good.
1√2 x plus IP,
Yeah.
and then you can take out the 1, 2's.
So, one thing that you should remember that we didn't prove this, but you should, you should know this either from earlier or you will know it now and prove it yourself. The commutator is bilinear.
Yes.
It's linear in each entry.
And then you just like do foil or whatever it's called.
Yeah. And you can do that just because it's bilinear. It's linear in each entry.
And then these are always gonna be 0, and then this one here, I have to make sure I don't mess this up, is No wait.
Is that right?
I mean,
Shouldn't it be the other way around?
no, it looks right.
Oh.
If you had P and X. Actually, maybe it should be the other way around because you want A with A dagger.
Yes.
No, sorry.
I've messed
In
it
the
up.
beginning, yeah, that plus and minus there.
Oh yeah, then.
And then you
this
switch it there as well, so you are consistent. Plus and minus.
Okay. Now that will be X up here.
He just
Yeah, yeah.
messed up the.
Yeah, and then minus I. Right, this is
Yeah, it should be minus I
Yeah.
PX now.
minus I. Oh no, that's right.
That was
and then
minus I PX. Yeah.
Okay. And then we have
and then,
these from
and
there.
then you have also
Yeah. PP.
yeah.
Because the I will become
Yeah.
-1 and then.
Good.
Okay, and then this is 0. This is 0.
Stop. Question for the audience. Why are those things 0?
X squared minus.
Yeah. See,
I mean, that's I don't understand.
it's like a trivial question, but clearly they don't
What
understand.
was?
Yes.
X squared minus X squared.
Yes.
P squared.
Remember, what is the commutator? Commutator, first thing and second thing is, write down the definition of the commutator somewhere much earlier, somewhere on the left side maybe, on the very left side, on the very left side.
Oh, matching. We're just matching terms.
The commutator is what?
AB
It's
minus
AB
BA.
minus BA. So what is the commutator of X with itself? It's X composed with X minus X composed with X.
Commutes with itself.
Yes.
Oh, those are commutators themselves. Ah,
Yes.
Yeah, we
wait.
disperse the commutator. Yeah.
Ah, that's interesting.
Okay.
Okay, and then we know that this is I because we showed this before, so that's -1. Wait.
No, X with P is minus is plus or minus?
I think there should be a negative here. And this one should be positive. Yeah, so then that would give us 1 plus 1
hold on.
again.
Wait.
Yeah. I think this is right.
No, you are supposed to get 1, but it's just give me a moment.
Yeah.
Did I? Yeah, so X with P should be IH. So you want A with A dagger, so it should be plus with minus. And so when I have,
Yeah, because it's.
Yeah, so-
This is right?
hold on, I have X with P, that's a minus. Yeah, X with P should be minus because I have a minus sign.
Yeah.
And then, yeah, that's right.
Okay, cool. And then that's 1. So we'll write this down over here.
That's right.
We can keep it.
Okay.
Yeah. So I think if you put the units back in,
It gives you H.
yeah, you'll just have a factor of H bar
Yeah.
or something like that.
Yeah, that's how I originally H bar. And then now what we're gonna do is we're gonna.
Yeah, hold on.
Oh.
Yeah.
This just shows A and A dagger commute.
No, if it was
No.
commuting, it would be 0.
Yes. This shows that A dagger minus
Difference.
A
Is
dagger
the
A
identity.
is equal to the
Identity.
identity operator.
I guess I should probably write it all identity instead. It's looking better.
I have two operators, I
Yeah.
compose them, I subtract them, I get the identity operator.
There would be a scalar of H bar if we didn't
Mhm.
change the units.
One fun thing is, and this is something I actually embarrassingly struggled with in fourth year. Is this ever possible in a finite dimensional vector space? That you have two operators, and their commutator is 1.
No,
Why?
because they would share. Because then, wait, would that give you 0 equals 1 or something?
That's the right idea. Do you guys know about trace?
Yes.
Yes. So you may recall that trace is some linear map from matrices
Oh yeah,
to
you get
whatever.
0 equals 1 and take the
Yeah,
trace of both
exactly. If
sides.
you were to
Yeah.
take the trace of this, if these were like over a finite dimensional vector space, and I had some operators A, B is equal to the identity, if you take the trace of A commutator B, that's the trace of AB minus BA, but you might know that trace is cyclic, so trace of AB has to equal to trace of BA, You can just check that. And so you get trace of AB minus BA, that has to be 0 because those traces have to be equal, equals to n, because the traces I add up the values under the n.
Yeah.
So this is not possible for a finite dimensional vector space. And for some reason in my 4th year I was like, there was a question which essentially, like, the answer was essentially you can't do it because of this trace argument. But for some reason I just didn't see this trace argument, and it was very embarrassing.
Wait, is this spare cup here?
No, I didn't have time to get it. I could get it. If you want to struggle alone. Okay, you know what? Yeah, let's make it more fun for me.
Okay, the next part's easy. It's just algebra. I got this unlocked. Okay, now we're gonna take these and we're gonna just rewrite them for x and p. Honestly, it's just algebra. Like, you guys got it unlocked, so I'm just gonna write the answer. Actually, I'll show the work. It's like not that hard. Okay, so I mean, just a bar, right, is equal to x over root 2 minus I p over root 2, and then that just implies that I p over root 2, sorry, x over root 2 is equal to a dagger minus plus I p over root 2, right? And then just replace that back into here. So that will give you a is equal to x root 2. What if I did it wrong? Am I tripping now? I might be tripping now. My bad. A dagger is equal. Oh, this is a negative.
No, is it?
What the hell did I do? It'll work out. Okay, and then yeah. So then that's a plus I p over root 2 plus I p over root 2. So then, oh yeah, this works out. Okay. Just move this to the other side. A minus a dagger. Then there's going to be a 2 here, and then it's going to go to the other side. So then you just root 2, and then you're dividing by I, which is just negative I. Does that make sense?
So what is this?
This low. Oh, I lost.
Instead of, there's little space there. Yeah, there we go. You can figure it out.
Okay.
And what was the result for x?
I haven't done it yet,
Oh.
but can I just write it? I feel like it's like.
Did you just say the answer? Yeah.
Yes. There you go.
Okay.
Should I write
And
this
I
here?
think these answers you should write there.
Yeah.
And also, instead of having minus I outside, you should bring the minus sign in and swap the order of a dagger and a.
Ah, right.
So it looks pretty good. Right, we've all solved a
Linear system.
two by two linear system before. If you really wanted to, you could write matrices for this, right? You can see that it's some change in basis.
Okay. Now, what we want to do is we want to take this Hamiltonian and we want to rewrite it using a dagger and a, because it just like simplifies really nicely. And I'm going to work backwards because it's easier to do. Can I do that, or is that cheating?
Sure, you can also just write down the answer and explain how
Okay,
the
fine.
answer would work out.
So the answer, I guess I should probably write it here, is equal to a dagger plus, nope, I did that wrong. A dagger plus 1/2. And then it's also useful to know that minus 1/2. And this this obviously follows from here, because you can just move this to the other side, becomes 1 plus thing, and then it's 2, and then put it back in.
Yes.
Get that.
Another way to write it actually equals a dagger. Actually, maybe write this on the other board. So you can write that h is equal to. What should this be equal to? 1/2 a dagger a plus. Yeah, a dagger a plus a dagger, right? Is that right? There should be a 1/2 outside the brackets, right?
Oh yeah.
Yeah.
Wait, is this true?
Up to some scaling factor, that's true.
Okay.
Why is that obvious?
I think you just swapped it.
Why is that obvious? So you had what? You had x squared
Yeah.
plus p squared, right?
Yeah.
X was x minus ip, p was x plus ip. Do you agree? So I'm doing a plus b squared plus a minus b squared. Do you agree? So what should I then be left with? Is it plus a minus b squared or minus a minus b squared? Oh yeah, sorry. It's x, yeah. It's plus, but then one of them has an I. Right? So it's I'm doing a plus ib squared plus a minus ib squared. So I should get that I should only be left with cross terms after after I'm done the calculation of the m. Somehow, right? Like this really should like be semi-clear from
Yeah,
this
like the
picture.
squares like cancel out, and then
Yes,
the,
and I'm left with cross terms.
yeah.
But now the important thing is that, you know, if you were just expanding brackets, you'd write like 2ab, but you can't do that because here the order in which you multiply things matters because the operators don't commute.
Mm-hmm.
Okay? And actually you remember, you know, if things don't commute from last time, actually these aren't self-adjoint, so you don't have it. But remember last time we had like uncertainty principles for things that commute.
Okay.
That's unrelated to it.
Okay. Now we can actually find the eigenvectors because
Yes.
it's just a little
Well,
simple to work. But
not-
there's like
not
some
quite.
things we have to prove first.
Yes.
Yes. Okay.
I guess you can erase this on the side of the board now and you have all the results.
Okay. First thing we need to show is that, or argue.
So let's motivate this first a little bit. Right?
Okay.
What we wanted to do is we wanted to find the eigenvalues and eigenstates. Do you agree? I told you do this kind of weird transformation. Okay, for whatever reason. And remember, we wanted to find eigenvalues and eigenstates. So perhaps what we should say is what? We wanted to find eigenvalues and eigenstates, right? And I gave you this new basis of a and a dagger. So what's one thing to try and check and see if anything interesting happens? I mean, he kind of knows the answer. So I want to find the eigenstates, and I have these new operators. What should I do?
You could look a guess.
Yes. Once again, you should find a clever way to put the words that I said and say them in a different order. That will be the answer. The words should involve eigenstate and then like new operators.
Nah.
What can I do with an operator and the state?
Apply it.
Great suggestion. So, which eigenstates am I interested in again? The eigenstates of?
Lowest energy.
No, I want all. I want all the eigenstates of this because I'm just solving this model exactly.
No.
So I want all the eigenstates. So I want to say, I want the eigenstate of which thing, of which operator? H. That's right. I want the eigenstate of H. And so now the question is, okay, I have these new A and A daggers. I wrote everything in terms of the A and A daggers. Let's just suppose something is an eigenstate of H. and apply an A on it and see what happens. That's roughly the idea of what is about to come.
Yeah, so basically what we're going to show is that if you have an eigenvector, yes. Yeah, if you have an eigenvector of H, then it's also going to be an eigenvector of A dagger A.
Yeah. I mean, that's something you don't even need to prove. That's something you can just say. So actually, sorry, I'm jumping ahead of myself. I'm very sorry. What the first thing was to say is like, we want to find eigenvectors of H, right? I want to make the problem simpler. H has this 1/2 factor, right? But that 1/2 factor, this is 1/2 times the identity. Do you agree? So if something is an eigenvector of this, it's still going to be an eigenvector of just A dagger A. So maybe you should write this on the new board that eigenvectors of H are the same as the eigenvectors of. Oh, that's a really pretty color.
Yeah, so lavender.
Almost as if I got them. Of H are the same. Don't write the words are the same. Do a double-sided arrow.
Comma if and only if.
Something like this.
I don't know. I wrote some. I think it's because they commute, right?
Well, because the identity commutes with everything.
Yeah.
Yes,
Oh
that's
yeah,
right.
AI.
And that's true. It is also because they commute.
Yeah.
But in this particular case, it's because when things commute, it's this is not necessarily true because of reasons which would be another presentation, like another reading
Oh, really?
session if we had more time.
Oh, I thought okay.
Yeah, that's right. So instead, let's find what's the difference between so the eigenvectors are the same. What's the difference between the eigenvalues of one and the other?
This part's actually kind of sick. I'm not gonna lie. Okay, so yeah, we want to find out like if what the eigenvalue actually is. So if we have a suppose, yeah. So
No, hold on. This isn't the question I asked.
Oh.
I said if I have eigenvectors of A, and then instead I'm saying they're the same as the eigenvectors of A dagger A. Okay, but what are the eigenvalues of H versus the eigenvalues of A dagger A? Question for the audience. Trivial question. Go ahead. Answer.
Minus 1/2.
Yeah, they're the same. They're just shifted by a half. Do you agree?
Right?
Yeah, that's it.
I'm not sure.
And so what did we just do? We just shifted the energy by a
half.
constant.
Oh, by
Right?
constant.
Remember, you can just shift the energy by a constant, and that's why you can do it in quantum mechanics. Do you agree? Because the eigenvectors are the same. If I shift my energy by a constant times the identity, the eigenvectors will be the same because the identity, everything is an eigenvector of the identity. And then,
Weird question. What units are we using?
we're using units where h bar
H bar
omega
double.
is equal to 1.
Okay.
Yeah.
And also x is rescaled in some weird way. Which we didn't write down here because whatever.
Yes. Okay.
Good. So now go ahead.
Yeah, so show that. Okay, now we're gonna show that if
This, I will give it this, is an eigenvector. I'm just gonna write EV.
of A dagger A.
So I think you should write sentences like this, starting with the word suppose. Because we're supposing this. This is back to the idea that I said, I have these new operators, let's see how they would act on the eigenvector.
And we're gonna show, a little weird.
We're gonna do it as a team. That A plus A dagger.
Of that is also an eigenvector.
Okay.
And is it eigenvector? And we're gonna find the eigenvalue of this eigenvector.
Because the eigenvalue is not the same.
Yeah. So we could just plug some stuff in. We're gonna do H A dagger.
Because we're trying to show that this is an eigenvalue. That makes sense, right? My bad. But we're gonna use the h of the other one. So we're gonna, which one do I use for this? I use this one.
Write the one that has less. Write a dagger a. Instead of h, write a dagger a without the half.
Without the half?
Yeah. I mean, the whole point of finding eigenvectors of h versus eigenvectors of a dagger a, the whole point of that statement was to search for eigenvectors of a dagger a, so you don't have to write down a random 1/2 everywhere.
Yeah, but won't the eigenvalue depend on that 1/2?
It will just be shifted by 1/2.
Okay.
I can just add the 1/2 at the end. That's the whole point. So that I have to, you don't write as many letters.
But we're trying to find the eigenvalue, no? Right. Maybe I'm
Lots of-
tripping.
First, you want to show that this is an eigenvector of h.
Yeah, but can't we do it in both at once? Can we
Yes,
do it that way?
but there you have to write an extra 1/2 I, and there you don't.
Okay.
Don't write an extra letter. Or at least I don't want you to. You can if you want to, but not right now. Okay. And now what do we use?
Do we use this?
That's absolutely correct.
Yeah. So we're gonna replace this with I got this 1 plus that.
Beautiful.
Is that wrong?
Actually, yes. Because you don't want to swap a dagger and a, you want to swap a and a dagger. Why? Because you want to have a dagger. What you want to do is you want to commute it such that you have a dagger h psi alpha.
Yeah.
Do you agree? Well, this way you commuted it, you didn't get h anyway. Do you agree? I still want to have h. I still want to have a dagger a somewhere. Here you have a dagger. So you want to swap the a and the. So
Oh, these ones.
these two.
Yeah.
Yes. So that in the end you still get an a dagger a.
Yeah.
So.
And then the a dagger a is 1 plus a dagger, right? That is right. No. Yeah, there we go. Right. And then just disperse.
Yeah.
Good. This is
1
1.
plus.
Checking out.
A dagger a. What's that?
0.
No. A dagger a. That was my.
Oh, this is that.
This is the h now. So a dagger h. Psi alpha. And maybe you want to put brackets around the 1 plus a dagger h. They're all act on psi alpha. Good. Now, question. H applied to psi lambda. What is that? What was psi lambda?
Or
An eigenvector. And so H applied to psi lambda should be? H applied to psi lambda should be?
there's no just lambda.
Yes. Also, sorry, it's not 1, there's an
It's
A
zero,
dagger.
right?
Yeah, sorry.
There we go. And then you just
Now factor everything out.
Yeah.
A dagger.
Yep.
Beautiful.
So the eigenvalue is 1 plus lambda, right? Wait.
So what did we actually show?
We showed that this, if this is an eigenvector of this, then this is also an eigenvector and it has 1 plus.
Yeah, the eigenvalue is the
Eigenvalue.
old 1 plus 1.
Wait, I got 3/2 when I did it with the 1/2. Is there a reason for that?
Okay, 3/2.
Like I got lambda plus
Yes,
3/2.
you got lambda plus. No, you should still get lambda plus
1.
1. You probably just made a mistake somewhere.
Mm.
Because everything should be shifted
Yeah.
by 1/2, but the relative
The scalar
difference,
should still be
the
1.
difference between two adjacent ones should still be 1/2.
Okay. Yeah, I don't know where I messed up. And then you could do the same thing for A. Just yeah, it's the same process, but I think it's 1 minus, right?
I'm sorry, say that again?
Maybe you could do the same thing with A.
Yeah.
Yeah, but it's
Sure.
1 minus lambda.
Yes.
Okay, so should I write that over here?
Yeah, maybe you write it as like a statement. You know, if psi alpha is an eigenvalue, that eigenvector with. Don't even write eigenvalue. Right. What's the eigenvalue condition? That's right. Wrong. There should be an A dagger on the side.
Oh, whoops.
Right?
Yeah.
That's good. Very good.
Is that right?
No, that's not right.
It's the other way around.
It's lambda minus 1.
Okay. I'm gonna switch.
I either no. The first one's right. Lambda plus 1.
Yeah, I was just gonna like swap it.
The
around.
other one is lambda minus 1.
So that way it like lines up.
Yeah. So the idea is that a dagger takes my eigenvector and sends it to an eigenvector with an eigenvalue plus 1, and then A sends it to an eigenvector with an eigenvalue 1 less. Okay? And so these A and A dagger are called creation and annihilation operators. They're also called raising and lowering operators sometimes.
Mhm.
Why? Because one raises the eigenvalue,
Yeah.
the other one lowers the eigenvalue.
Yes. There you go.
And when I say that, I mean sends to an eigenvector with an eigenvalue that is 1 higher, 1 lower. Okay. So now, can people tell me what the hope is? What is our hope now? Now that we've noticed this cute fact. What can I hope for now? So, what do we want to do? We want to find all the eigenvectors and eigenvalues. Okay. I got this thing that I have this operator, which I know what it is. You know, I have it written in like x minus x. I know what the operator is. And I know that this operator can take one eigenvector, send it to another eigenvector, and it's going to have some other eigenvalue, and I know what the new eigenvalue is going to be in terms of the old one. So what can I now hope for in terms of, what's one strategy I can choose to find the eigenvectors and eigenvalues?
Build a really nice set where it's like 1, 1, 1, 1, 1, 1.
I think you're saying the right word. Well, I think you have the right idea, but you're not explaining it clearly. So that's the right idea. So
your turn.
yeah, that's right. So the hope is that you can.
You have a map that sends something to really close to something else. Is it like complete in some sense?
So that's kind of the condition that you want. But what do you want to try and do? You want to
Finding an eigenvector or an eigenvector and then applying a.
Yes, exactly. What you might want to do is you might want to say, okay, suppose I actually find an eigenvector, right? If I find one eigenvector, if I apply a dagger or a repeatedly, I can find a bunch of other eigenvectors
Yeah,
with
above
like
it, with
eigenvalues above and below. So now what's the question going to be?
Can you find one?
Well, okay, first question is can you find one? But then the other, arguably more important question is,
Can you find all?
yes, if I start somewhere, will that give me all the eigenvectors, or will that give me only some of them?
Is that like my question, like completeness?
Yes, but that's not completeness in the sense of a complete space. But yeah, like, this, we now have a clear strategy of how to proceed further from this. We want to find one eigenvector, and then find the rest of them using, by applying a dagger and a on it, but we aren't sure if that will give me all of the eigenvectors. So arching,
Yes.
what's the answer to that question? Will this approach give me all the eigenvectors that I could ever want?
Yes.
Yes, so that's the answer. Let's prove that first, and then we'll do the strategy.
Okay. Okay. First, what we're gonna show is we're gonna show.
I think you should stop and take a sip, because I just said a bunch of things,
Okay.
and so they're still writing it. So you should just take a sip. Oh, that's good. I don't even know what they're writing. Okay.
Do we know some initial eigenvector?
So we'll get to that. First, let's show that this kind of approach will give me everything I want.
Low key, I didn't finish the entire sheet.
That's fine.
Okay.
I don't care.
You did way more than me, bro. I got through like maybe like half of it.
I felt that this is about half, but okay.
We're near, bro. We're almost done.
We're almost done. But we didn't get to like,
The
we
sustenance.
didn't get to the punchline, you
The
know?
substance, yeah.
Yeah, we're just doing calculations for now. Okay, so let's go to erase this, and now let's do the next one. Okay, so at least we have a clear idea of what's going on. We want to try and find an eigenvector and hope that we get all of them this way. But first, we're gonna, show that we indeed get all.
Yeah. Okay. First, we're gonna show that the eigenvalues of a dagger a
Yeah.
are positive. This right here. One sec.
You should write down the statement you're trying to prove.
Okay.
If you're,
The
I
eigenvalue.
think you should just erase this
You're right.
and just write it. I'm being very controlling today.
You can't use EV anymore. Evals.
Usually people write eigvals.
Oh,
It's still long. But
Whoever named it should have made it shorter. The eigenvals of a star a are greater than 0 or equal.
Sure.
Does that work?
Yeah, that's right.
Okay, cool. So to do this, first we gotta recognize that this is equal to
Where psi lambda is what?
element of this.
No.
Oh, an eigenvector.
An eigenvector of that, but what kind of eigenvector?
With eigenvalue lambda.
No, not quite. With eigenvalue lambda, but what else? What else is true about psi lambda? Yes.
No, just general question. What guarantees that the eigenvalues of
Oh,
a dagger
oh yeah. It's that a is less than infinity, and then the norm of it
Is 1.
was 1. Oh yeah, 1.
How can it be 0?
My bad.
Yeah, and I mean, what is the norm? The norm is precisely that integral.
Yeah.
Yes. So it's a normalized eigenvector.
Yeah.
So why prove this fact for people? Why is this true?
It's just started L2.
Wait, do I do it or yes?
Huh?
The L2 bar.
Yeah.
What about it?
Square space.
you are.
all the size are elements of our Hilbert space. All of our Hilbert space is L2 of R. So all of my vectors are functions that are square integrable, like this, and the inner product, recall the inner product was the integral of f bar g or f g bar, whichever convention you choose. Yes. Okay, so prove this fact.
This is looking pretty like. Oh wait, like prove this fact.
Prove everything.
Alright, so
This, the reason that this is true is because
a bar a is equal to lambda this.
Yeah.
and then we can take the dot product of both sides apparently
With itself.
Okay, no. Erase. Sure, you can say it that way,
Yeah.
but because you're saying apparently, clearly something is not clear, so erase this.
This?
Yeah, erase that, and just continue the line above.
oh like y to 1
Yeah,
why
just
is-
continue
oh,
the line above.
This
Right?
is chill. You can move the a over here.
No. Sorry, no. That's not
Oh,
what I
that?
meant.
Oh, this line.
No,
That
the
one.
line above, the line as you were.
Okay,
Yes. Okay. Write down. Start equals. Okay. Open the bracket. Write psi lambda. Psi lambda.
Yeah.
Okay. But a dagger a applied to psi lambda is what?
Lambda.
Yes. Good. Close bracket. Good. Now you factor out the lambda,
And then this is 1.
and then that is 1. That's correct. So this is on the one hand side.
Yes.
So that's we proved the first equation. Maybe you would want to write lambda bar because you factored out of the second entry, but a dagger a is self-adjoint, so you know the eigenvalue has to be real, so you don't worry.
There we go.
That's right.
have we showed it's positive no
Okay, but yeah, so that's on the one hand side.
Yes.
On the other hand side, you do the thing you were going to do.
Okay, and then we can show that this has to be greater than 0, which is what we want, because you know that this is the adjoint of that, so you can just move it and take the adjoint, which is a.
Yeah.
Lambda.
Yeah,
and then that's 1 sorry that's
greater or equal to 0.
yeah
Well, this is like the definition of linear product space.
This is the definition of norm.
The
which
norm,
just
yeah,
follows
because
from
this
the
is,
inner product, from the inner product axioms or whatever. So,
Yeah.
okay.
bet I'm not gonna lie
Mm-hmm.
that's about as far as I've got
No, this is great. This is about as far as I expected you to get.
You expect them to go very far. Oh my god.
Well, he is the presenter, right? And he also
had a test today and a test
he had a
2 days
test today,
ago.
but he also spent a bunch of time chatting with someone to help them. Like,
Bruh.
this is good.
Don't
This
listen
is-
to him, bro. He did a great job. Thank you.
Yes. Okay. So let's see if we can get anywhere further.
I could read this
No.
Yeah.
Don't read it. I'll just ask you questions.
okay man
So, look, before we got what? We got that using these ladder operators, if I have a vector, an eigenvector, then there has to be another eigenvector with eigenvalue +1. And I also got that if I have an eigenvector, then there has to be another eigenvector with eigenvalue -1. Do you agree?
Mhm.
So if I have an eigenvalue, there has to be an eigenvalue lower. Do you agree?
No.
Okay. But that's a little strange because what did we just show? We just showed that the eigenvalues are always positive. Always positive. What seems fishy about this?
You can go negative. If you
Yeah.
keep going down, but
Yeah.
we said that they're greater than 0.
That's right. In principle, what could happen is I could have an eigenvalue and I could keep going down. Do you agree? Unless what happens? Unless what happens? What?
you go to 0
Unless you go to 0. What happens if I go to 0? If my eigenvalue is 0, do you agree?
yeah
then
Then this is 0.
yeah, then I get that A applied to psi of lambda is
Zero.
I get that A applied to psi of lambda is 0 at some point. Do you agree? So what does this mean about what the eigenvalues have to be? What
I mean,
kinds
I
of
have the
numbers?
answer. So I'm not
Well,
gonna
you
say.
have, yeah, so maybe give them a moment. Right. So I know I can lower my eigenvalue by +1 or -1. And we realized, wait a second, if the eigenvalues have to be positive, I can't, there's something fishy, there's some condition on this. And so if you look carefully, you realize, wait, if my eigenvalue is 0, right, then if I apply A to psi lambda, I should get the 0 vector and life is okay.
It's not much like work.
Or sorry, if I got,
This is it.
no, sorry, lies. If I applied A to, suppose lambda was not 0, suppose lambda was 1, I think, right? 1 or 0. No, I want lambda to be 0. So yeah, let's just prove this. So suppose lambda is 0, so we have phi 0. Let's apply A to phi 0, and there should be some obvious way to see that it has to be 0. Yeah, suppose lambda is 0, then let's apply A to phi 0. A to psi 0, yeah. Okay, we want to show that that's 0. So maybe let's do, yeah, you know what, let's apply H on the, as well. Yeah. This has to be equal to, okay, and then just expand it again. A dagger A, size 0. Yeah, and so now you want to do the you want to commute,
Jerry's the other one?
pardon?
Jerry's, oh wait, no.
Yeah, you want to commute one, it's 1 minus,
Wait, is it?
yeah.
1 minus a dagger times a.
Or, no, it's worse, it's a dagger a minus 1. Sorry, just look at the thing again, right?
Yeah,
And it's, yeah, sorry. Just write a dagger a minus 1 times a psi naught.
Wait. So this one a.
No, it was a dagger a. It was correct.
A dagger a.
Oh, then it
equals
should be a dagger minus 1. Yeah, that's right. A dagger equals a dagger. No,
Okay.
that was correct.
Okay.
Equals
Equals.
a dagger.
Okay.
Yes. Minus 1.
Okay. Yes.
A psi naught. Good. And now you want to commute again the thing. Actually, no, you don't. You're done. So just, yeah, that's good. So now you have A, but then you have A dagger A applied to psi naught. What's A dagger A applied to psi naught? Hmm?
1 plus 0. So 1.
It's just 0. A dagger A applied to psi naught is 0 by assumption.
Oh, a dagger a, yeah.
See?
Is a dagger a lambda?
Hmm?
A dagger a is lambda, but we said lambda 0. Is that right?
Yes.
Okay.
Applied to psi naught specifically,
Mhm.
right? So this gives me 0. And then I'm just left with equal to minus a psi naught.
Oh, which is only possible.
Actually, wait, sorry. Yeah, equals to minus a psi naught, right? However, this can't be, because I assume that, I didn't assume, I proved that
Something
my
is-
eigenvalues have to always be positive. Do you agree?
Square.
So this means that the only way that this is possible is that a psi naught has to be equal to 0. That's the only way this is possible.
What about a dagger?
What do you mean?
A dagger sign on.
A dagger sign out?
Oh, no,
I
sorry.
mean, that
Yeah,
raises the
raises-
eigenvalue, so
okay,
that
sorry,
might
yeah.
not be 0. Do you agree? So I get that from this condition, if I was to have, you know, something that has eigenvalue 0, then it has to be killed by A. Do you agree? And then you say the following, that, okay, if I had something that had an eigenvalue that was, yeah, okay, sorry. So this is something we proved. The eigenvalue is 0, then it has to be killed by A.
Wait, how do we know this exists, like for sure?
So we don't know. We say suppose that if
Okay.
it does. Okay. And then you say the following. Okay. From this I see. Okay. Suppose I did have something that had a 0 eigenvalue. Okay. Then I could go up with a dagger, right? And so I get a bunch of other eigenvalues. Now, you say, okay, so what numbers do the eigenvalues have to be?
One, like, what can I say?
We'll give them still a chance. What numbers do the
If
eigenvalues all
the
have to be?
eigenvalue is at 0, the
Yeah.
only thing you can do is apply a dagger.
Yes.
To go up, and anything else you can do either.
No, so suppose we're at 0, then what, if we're at the 0, what eigenvalues do I get? What kinds of numbers are they?
Non-negative integers.
Non-negative integers.
Ooh,
Good.
got it word for word.
Beautiful. So now suppose that, okay, so the question is that all the eigenvalues, right? Suppose I had something that wasn't a non-negative integer, so I had something that's in between an integer. Then what would go wrong? Sure.
You can go negative.
Yes, I could kind of keep going down, and then I'd eventually get to a point of something that's negative. Do you agree? And in that case, I think actually what would go wrong? I'd have the same calculation, but then I need yeah.
Energy quantized.
Yeah, so that's the other thing, is we see that energy is quantized. Actually, wait, let me see. If the energy was like fractional, I'd have the same calculation, but I'd have like.
Or not quantized. Oh, yeah. Quantized in the sense that they're like levels, because we have the
Yes,
we
yes,
subtract it
yes.
by half and
I
one
mean-
units, right?
I mean, it's still quantized. Even if you add the 1/2 units, it's still quantized. Sorry, I must have messed up here. There has to be I forgot to add this in the handout. So if it's 0, then we figured this out. But then if it's if I had a state that was somehow yes, sorry, let me just try and write this myself, just to see if I can get it right. So if, okay, so just compute arbitrary, right, a psi lambda, right, h applied to this, we got here that it should be, well, I mean, we got earlier, it should be lambda minus 1, a psi lambda. Do you agree? And okay, so I get, if lambda is in between 0 and 1, do you agree? Then that implies that a psi lambda must be 0, but I should get that I just can't have a lambda between 0 and 1. There should be some easy way to prove this. Okay, like sorry, I'm blanking, but there should be some contradiction to show that lambda cannot be between 0 and 1, and so I get that lambda has to be the integers. Sorry, I'm blanking on what the argument is. I'll add it later if I when I get to it. But that should be the argument, I think. And so now we know that, so the eigenvalues are all the integers. Do you agree? And if I had, if they're all the integers, not the integers, the non-negative integers, then I should have some state with eigenvalue lambda equals to 0. Do you agree? But now we can try and just solve for this, for something that has eigenvalue lambda is equal to 0. Do you agree? We can try and solve for it directly.
Ooh.
I just realized
Yeah.
that if you get 0 marks on the on a whole question on the 157, then you guaranteed like yourself like a 55 max.
Yeah. Yeah,
That's
that's
a
it's
rough
okay.
test.
We're okay. We were freaking out because this one test was really annoying, but it's okay. It's gonna be okay, guys. Question.
Yes.
Lambda contained within
What?
parenthesis 0, 1. Intentional? Parenthesis intentional, like it can't be
Yes.
0?
Yes, I'm saying that it shouldn't. That shouldn't be possible.
Wait, can't lambda equal 0?
Yeah.
So parentheses not including 0 to 1.
Oh, okay. Oh, yeah, wait,
Interval,
yeah.
interval.
Cannot.
Not including 0, 1.
Okay.
It should be able to. There should be some argument. I don't.
Oh, and then if it's not 0 to 1, then it can't be any like decimal, basically.
Yeah, so it can't be any decimal. It has to be in the integers. I think that's true. I just can't see the argument. Okay.
No, they got it perfect. They got it.
I'll you know what, I'll just finish the rest so we're not here forever.
I bet.
And so no, this was pretty good.
Do you want to switch my
Um,
Oh yeah.
oh yeah,
Notice?
sure. Yeah, I will. Yeah.
Wait, Loki, can I sit here? I kinda like this.
That's fine. Yeah, go for it. So okay, so we let's do a quick recap of the logic. So first we said, okay, we had H. I wrote it as A dagger A plus 1/2, right? Something like this. Then we said that eigenstates of H are the same as the eigenstates of A dagger A. Okay, do you agree? Then showed that if lambda is eigenvalue of A dagger A, then lambda plus 1 and lambda minus 1 are eigenvalues of A. Do you agree? Then we showed, like separately, that lambda is always greater than 0. So this is for eigenvalues of A dagger A. Do you agree? And then, so a bit fuzzy, but concluded that the eigenvalues of A dagger A are the natural numbers union 0. Or at least a subset of this. Okay. So now the argument is, okay, suppose I find an eigenstate with eigenvalue 0. Do you agree? Then I should be able to, and suppose there's only one eigenstate with eigenvalue 0, then I should be able to build all the rest of them above. Do you agree? Okay. So let's do that. So I want to solve A dagger A is equal to 0. A dagger A applied to some psi 0 is equal to 0. I want to solve this. Do you agree? But what is this equation secretly?
H.
Hmm?
The Hamiltonian.
Well, this is not, it's H with a half shifted.
Yeah.
But what is this equation? What kind of equation is this?
Those.
Yeah, those, but what kind of equation do I get in the end? Psi is what kind of object?
Vector.
No, but
Function,
yes,
a
but it's a function. So this will give me some differential equation, which I
Oh,
should be able
yeah.
to solve. Okay, so I have 1/2 x so minus plus minus the derivative of x times composed with x plus the derivative of x
Oh, I forgot to write that down.
applied to psi 0 has to be equal to 0.
Oh,
Do you
that's because
agree?
the h's go away, right? Because they're one on
The
P.
h's, what do you mean the
Like
h?
the p is becomes just
Yeah, the h bars go away. That's right, because I set h bar to 1.
okay.
In reality, the solution will have a bunch
Oh,
of
and
factors
then the
of
I
like.
cancels out when you put in p.
Yes.
Okay.
The point is that in reality, all of these solutions will have a bunch of like m's, omegas, and h bars everywhere, but I don't care. Like I want conceptually the idea to be clear. So let's expand this. So I have x squared psi naught.
What about 1/2?
Hmm?
The 1/2.
Oh, I forget the 1/2. It's equal to 0, so I can multiply by 2. So I have x squared psi naught minus partial x squared psi naught. Okay, and then I have the cross terms. So I have minus partial x of x psi naught plus x times partial x psi naught. And this whole thing has to be equal to 0. Do you agree?
Mm-hmm.
This is some differential equation I want to solve. Very good. Now maybe I want to expand this.
Product rule.
Yeah, product rule. So I have minus squared psi naught plus x squared psi naught. And the product rule here goes like what? I have the thing that hits this guy gets cancelled with this. So I'm just left with minus psi naught equals 0. Is that right? That looks right.
So negative.
Yeah, that looks right.
Where are you gonna?
Okay, let's see if I can solve this from first try. I think I roughly know what the answer should be.
Do we factor out the sign on like the?
So yeah, so this is what we're going to do. We're going to do partial x squared psi naught is equal to
1 minus x squared.
yeah, 1 minus x squared psi naught. Okay. Okay, and I just know the solution to this, and I'm just thinking.
This is
about-
just a harmonic oscillator. It's like that's the point.
No, no. The harmonic oscillator had the harmonic oscillator was what? It was x doubled up is equal to minus kx.
Yeah.
But here I have an x squared.
So we're looking
so
for a
this is much
function
more
that's
complicated.
second derivative is equal to itself times 1 minus x squared.
Yes,
Okay.
that's right. We're looking for a function that has this property.
And that's the low energies, the
And
zero
this
energy
and that function will be the lowest energy eigenstate. And then I know that to get higher energy eigenstates, I want to apply a dagger to it. But a dagger, I know what it is. It will just be some like taking a derivative and multiplying by x and adding in some way. Okay. That will be.
Where do these come from? The a dagger and a
In what sense?
like how would like we kind of
How did this idea originate? Of like we could
Where
take
did
two
the-
random
it's a
things,
one
slap them
over
into a
root
commutator.
two.
That's a good question. I think the idea is more like I want to write down two things such that their commutator is a real number. Sorry, such that their I want to write down something such that its commutator with a Hamiltonian is a real number. That's the main idea. That's why all of this works. Because the commutator with a Hamiltonian is, if you have anything where the commutator with a Hamiltonian is some real number,
It's 1/2 here, right?
in this case it's 1.
Oh yeah.
Right? It was yeah. If I get something that the commutator with the Hamiltonian is 1, then I know that if I apply that thing to an eigenstate, then I'll get a new eigenstate with eigenvalue 1.
You want a recursive process.
Yeah, I want the recursive process itself. And this often appears that you want to take something and find operators such that if you commute it with a Hamiltonian, it's not. I'm telling you lies. This is wrong. What you want is you want to find some kind of operator, whatever, C, such that H commuting with C is some constant times C itself. Okay? And from that, this condition is what gives you that C sends an eigenstate to another eigenstate with some eigenvalue shifted by K.
It also gives you uncertainty on those operators.
It does not.
Wait, then what did I do?
You did, the commutator had to be a constant real number, or just a constant number.
Constant.
Not real number, just a constant number.
Is
Here
A-
C is an operator.
Ah, okay.
So this is not the same, right? Because we got that, you showed that A dagger A with A, the commutator was minus 1A.
Yeah.
Is that like x to the e x cubed? Something like that?
That's right, it's x to the e x squared. Sorry, x to the x squared. Or, no,
No?
x to the x squared, no, it's just e to the x squared.
Oh,
E to the minus x squared
okay.
over 2. So it should be a Gaussian.
Okay.
I think.
That was close.
Nice.
Well,
Ah.
sure.
No, but the fact
Um,
that is nice though.
How do you solve this if you were to do it properly?
Wait, there's a real
not
method. It's
sure.
not just guess and check.
No, there are there's actual methods to solving ODEs, and maybe I
Yeah,
should
you
have
can just
listened.
plug it into Wolfram.
Yeah, sure.
That's
But
my
I
favorite
should
method.
I should be doing better with this.
No, I mean the point is to get some like probability distribution graph and probability distribution, right?
Oh, I'm starving.
That's the nicest one.
Oh wait, sorry. There is one way to do it would be to maybe try and have something like this sends it to 0, this sends this to 0, and then try and
Like what do keys are the partials?
yeah. Sorry, sorry. I can yeah. Sorry, this is the better way to do it. I'm being silly. You want to solve this applied to this sends to 0. Do you agree? This means that this has to send this to 0. Do you agree? Okay. So then let's relabel this as I don't know, phi of x. Okay, and then let's solve for x minus partial x applied to some phi is 0. Yeah, this is the right way to do it. Okay, and so then this just means partial x of phi naught is equal to x phi naught. Do you agree?
Yeah.
But what function does this? Okay, this is easy to solve. Maybe people know how to solve this. There's one way to. There's kind of two ways to solve it. One is to write down the answer, and then there's one like.
There's a way to solve it.
Yeah. So.
Oh, you move it to the other side.
Yeah.
right?
So you can do. So this is what this is.
F prime minus f.
F prime. I can
minus
divide
x.
by phi naught, and I see that this has to be equal to x. Do you agree?
So the derivative divided by itself. Is
Yes. But now I can integrate both sides by dx. From say, let's go from 0 to whatever x prime. Sorry, dx integrate with respect to like this. Yeah, that's right. I can do this. Do you agree with this?
Yeah.
But what kind of integration can I do on the
U-sub.
side? I can do a u sub. Very clever. And so I get from 0 to phi of x. Sorry, phi of 0 to phi of x. D phi 0 over phi 0 has to equal to, and then what's integral from 0 to x of x prime dx prime?
1/2 x squared.
Yeah, 1/2 x squared.
But you know I put the derivative of 1 is x on the test today?
Don't worry, bro. We all did some shitty ass thing.
Okay. What's the integral of this?
That curve.
1 over phi naught d phi naught.
Log.
Log. Beautiful. So I get log of phi of x minus log of phi naught. Phi naught at 0.
Which is 0, right?
Not necessarily, but is equal to 1/2 x squared. Do you agree?
Yeah.
But now, how can I solve for phi of x?
Do
So-
take both to the power e.
Yeah. So I get
I'm on a roll, bro.
that phi of x is equal to phi naught times e to the, sorry, there should be a minus sign somewhere maybe? Or no minus sign? No minus sign. Okay, let's hope that this works out. 1/2 x squared. Is that correct? Maybe. I think there has to be a minus sign somewhere.
It's because it's the absolute value.
No. Ooh. Is this right? Is it x minus delta x or is it x plus? Oh, sorry. This is true. A dagger minus I minus 1. No, yeah, plus. There should be a plus here in the end, no? Because I have minus I times.
But then the other one would just be negative.
Oh yeah, sorry. No, that would be fine. Sorry. Minus. Oh no, sorry. Yeah, this is correct. Okay, maybe that's right. Okay, sure. And then the next ODE that I will want to solve is do, some constant e to the 1/2 x squared has to equal to, has to equal to x psi plus psi prime. Is that right? Yeah, that's right. Yeah, so I got that, like, if I apply this to this part, I should get 0. And so I got that then this part has to be equal to this. And so then I now have to solve this equation. This equation is a little harder to solve.
I mean, you said this would be much easier.
Hmm?
You said this would be easier for you.
Well, this is kind of easier now to solve than this, because for this I know standard methods to solve this.
Do you think you could have solved it from the original?
From the original directly?
Yeah.
Oh, from the original directly? From the original directly, you'd need to solve for arbitrary energies. And what you, okay, I won't talk about this, it's taking a while. But essentially you'll get that the ground state should be something like some constant times e to the minus x squared over 2, and maybe you'll have some factors over here. And this is just the ground state.
Yeah.
I need to apply the creation operator
That one,
to
yeah.
get the higher states.
Okay.
But how is it going to change? Look, how does the derivative affect e to the minus x squared?
Is it going to change by a degree of x?
Yeah, you get a degree of x, and then if you multiply by x, you get like just a constant. And so then you get like some polynomial times e to the minus x squared over 2.
Yeah.
Okay. So all the higher eigenstates are going to be some complicated polynomial times e to the minus x squared over 2. And figuring out what that polynomial is just by doing that calculation is kind of hard.
Oh, actually.
Out of curiosity, none of this is actual practical work. We're still very theoretical right here.
What do you mean?
Wait,
Like,
didn't we
we're
just
not gonna
solve
be,
the
yeah, exactly.
oscillator?
We're not actually gonna be given values to plug in and generate a like probability distribution graph with like numbers.
What do you mean? What's the question?
Avoid the question.
There is no exam for this course. I don't know what you're asking. But look, okay, if you then did all of this whole computation, all of these arguments,
Yeah.
well, you don't have to do the arguments. You just kind of have to do compute the commutators again without doing the rescaling. Actually, you can define the A and daggers with like some square root of m omega over h bar or something to get the right, the same commutation relations. And so you can find the eigenfunctions to be exactly whatever they need to be. And then you get that the energy eigenvalues are h bar omega times integer plus a half. And so that, I think, agrees. I don't know what experiment you would do where you see this. But actually, a particle, so I won't explain why, but a particle in the magnetic field, that actually can be described, that can be mapped onto a harmonic oscillator problem. And so actually, and you can do an experiment and see that these are indeed, for a particle in a strong magnetic field, that these are indeed the right eigenvalues for that kind of problem. So what we did is actually a reasonable calculation. But the big idea that you saw today was that you have these kind of energy levels, which I can index by the integers. Okay, sorry, 0, 1, 2, 3, whatever. These are always spaced from each other by h bar omega, and that if I want to go up, I go up with a dagger. If I want to go down, I go down with a. Okay.
Do they occupy all naturals?
Yes. Well, because look, I showed you that there's a ground state at 0, so I know I can get all the natural numbers above just by applying a dagger. Now, one thing to note. So, right, final comment. You should write this down. So let psi n be the nth eigenstate, the normalized nth eigenstate. Okay, then a dagger applied to psi n should give me, I think it should give me n plus 1, but there should be a factor of like root n plus 1 here. Yes, okay, and then this would complete the whole discussion for me. Right, they map it to an eigenstate, but the eigenstate is whatever. So let me just double check that I am getting the square roots correct. Sometimes I can make a silly mistake like this, and it's just easier for me to not think about it. Oh yeah, I made a mistake. Or no, this one is correct, and oh, this one's also correct. No, it's not correct. N plus 1. Okay, it's still n plus 1. Psi n sends to n plus 1. A n gets sent to, yeah, so, yeah, that's right. Alternatively, the bottom one you can write down as good. Yeah, you can write this down either way. Oh, sorry, n minus 1. There. So this is just to say that when I apply a dagger, it sends it to an eigenstate, but it's no longer normalized. It also scales it by something, so you can normalize it. Okay, and so from our calculation, you can believe that this eigenstate will be some polynomial times e to the minus x squared over 2. Okay, and these polynomials, I think, are called the Harmonic polynomials. Let me double check this, if those are the right ones. Can I find an article?
Time is it?
A minute. It's time to stop.
I might have to leave some for me.
Yeah. Let me just double check this. Yeah, Harmonic polynomials, that's right.
Bad.
So these polynomials have a name and they're well studied, whatever. And so these polynomials, they have like some non-trivial recursive relation, which you can figure out if you, well, you can now figure out these polynomials by figuring out how the derivatives for them should work out, whatever. But I don't want to. Okay. Yeah, but now you've solved the harmonic oscillator. This is like the classic example. And so this idea of having ladder operators that let you hop between energy levels, that is going to appear again and again and again.
Does that appear in the electron too?
In the electron, in what? In the hydrogen atom?
Yeah.
No, not quite. There you have a different equation, you have a slightly different solution. Because that one's really different from the harmonic oscillator. One thing to know that all of these energy levels are equally spaced.
Mhm.
Do you agree? Remember when we had particle in a box, we had 1 over, was it n squared or 1 over n squared?
I don't
You
know.
said the same thing.
Huh?
1 over n squared or 1 over n squared?
N squared or 1 over n squared? N squared
I'm deaf.
or 1 over n squared, okay.
I'm deaf.
But
You
yeah,
said was
essentially-
it n squared or 1 over n squared, but you heard 1 over n squared or 1 over n squared.
Yes.
I'm deaf. I'm
And
sorry.
so okay, whichever one it was, I think it was n squared. I should really know this, but it doesn't matter. The point is, there the energy levels were not equally spaced.
Mhm.
Here the energy levels are equally spaced. This is a key idea. You still get the energy levels are equally are quantized, and you also get this ladder operator theme. Okay, very good. Yeah, let's stop here. This was fairly long.